Hello, Rajamani. I'm Tony.
Oh, hi, Tony. How are you?
Fine. Alive.
Okay, so welcome to our Monday seminar. Today we are very happy to have with us Rajamani, who is going to tell us when and how QED in 3 dimensions can be seen as a conformal field theory. So please.
Thank you. Thank you. So first of all, I should thank you for remotely inviting me. You know, this is hard times, and I very much rely on going to meetings on a regular basis because when it comes to physics, I'm quite isolated. I am the only particle theorist in the university, and unless I visit places, I don't get to talk to anybody, basically. So thank you very much. So this is actually a sort of a developing story. So what I thought I would do is, instead of just talking about the paper that Nikhil and I just wrote, I will give an overview of what happened before that to give motivation as to why we decided to do this. So So this is, as I said, in collaboration with Nikhil. When we were working on this, Nikhil was actually a postdoc in Brookhaven National Lab. But in the midst of all of this, his time ended in Brookhaven and he had to move to Jefferson Lab. But he physically didn't move. He is still in New York, but he had to get an apartment in Newport News just to say that he is there. That's the way it is. But he is working remotely. The main reference, which is why I think you were interested in listening to me, is this one. But there are background references. The background references actually start out in 2015, which is when Nikhil came as a postdoc to FIU, and we have worked on it from then on. And I have to tell you that the basic idea for this paper, which means this 2009 paper, comes from Nikhil, because after we realized it's a conformal model, and after reading several papers, going all the way back to Appelquist's paper on QED, to papers that Klebanov and collaborators have written, and many others have written, we thought that it might be interesting to try to see if there is a way to do so what we call as conformal QED. So the basic point is this. When you do, I'll show you this result. When you do QED3, mainly numerical simulations, you find that whereas the short distance behavior is governed by the coupling constant, and it's a free field theory, the long distance behavior seems to be conformal field theory. Well, conformal probably is an exaggeration because we have not shown that it's conformal. What we have shown is it's scale invariant. So that being the case, we were wondering if there was a possibility to write down a model so that there won't be a separate UV and an IR scale, but rather it will be conformal on the lattice without any fine tuning. So that's the point, okay? So the basic thing here is two-component massless Dirac operator in 3 dimensions, and it's in an abelian gauge field background. We have done work on non-abelian theories, but I won't talk about it today. So the Dirac operator has the 3 Pauli matrices, and I work in Euclidean space, and this is the covariant derivative, and the gauge fields are basically real numbers. And just to make sure that we have the notation straight, because there is some confusion when it comes to QED, I talk about 2-component fermions, not 4-component. Okay, so it is irreducible. Okay, there is then a parity, which everybody knows, which is taking x to minus x and the gauge field to minus a, and then in that context, C goes to C dagger, but because C dagger is minus C, Formally, you say parity is a symmetry because determinant of C is determinant of C dagger in this particular case. But if a regularization is used that preserves gauge invariance, as you know very well, the determinant is not parity invariant. You have the determinant of C dagger is the determinant of C times a phase, and the phase in the typical normalization has eta of A. Eta of A, people typically write as a simple Chern-Simons term, but it really is not a simple Chern-Simons term. It's a little bit more than that, because if you're using fields that are not perturbative, it looks different. But the main point is it is gauge invariant and it is a phase, right? So how do we do the lattice formalism? There are many ways to do the lattice formalism, but it turns out the cleanest way to do this, I will tell you why, is to use overlap fermions. And in overlap fermions, the main thing this also causes confusion when I talk to people outside the lattice. So on the lattice, fermions always see compact gauge fields. It's possible to write down lattice fermion gauge action so that it is non-compact, but it's almost never done. So the gauge fields are always compact from the viewpoint of fermions. The action for the gauge fields, that is the gauge action, you could decide to put it as compact or non-compact, and in 3 dimensions it matters. It depends upon whether you want to suppress monopoles or not. So you have a control on whether you want to suppress monopoles or not whenever you study these theories. The fermion generating functional in a fixed gauge field background looks like this. It has a determinant, which is the fermion determinant, and then it has a propagator. That's it, because it's bilinear. So the regularized unitary operator V plays the central role, and that depends on the background gauge fields. Now I'll briefly tell you how you construct the V. So the parallel transporter on the lattice acts on a field by a compact U1 gauge field. So UK, you should think of it as e to the I A, where A is the one that I wrote down before. But from the fermion's viewpoint, it's U. Oh, by the way, I should mention, you can stop me anytime and ask questions. It doesn't have to be at the end of the talk. Okay, any little thing that confuses you, please go ahead and ask. TK is a unitary operator, as this is pretty standard. Under parity, TK goes to TK dagger, and under gauge transformation, TK goes under a conjugation G, TK, G dagger, where G itself acts by the gauge transformation. Okay. Now, the naive Dirac operator is you just take the polymatrices and multiply it by the derivative TK symmetrically TK minus TK dagger, and then you know D dagger is minus D, and it looks like parity is preserved. But the reason why parity is preserved is because naive Dirac operator has more than one flavor, and you have sort of, it has always an even number of flavors, and you have worked it out in such a way that parity anomaly cancels between a pair of flavors. Now, Wilson mass operator, which you need to lift the doublers, looks like that. And the Wilson mass operator is also B dagger as B. Now, the interesting thing when you do this is you can write down the Wilson Dirac operator in 3 dimensions is actually a 2-component Dirac operator. Okay, this is important. It's not Hermitian, because D dagger is anti-Hermitian and B is Hermitian. So it's not a Hermitian operator, but you can write down a one flavor fermion in 3 dimensions, which is 2-component. This was done long time back. This is a paper due to Costa and Lucier, who then figured out how to get the anomaly from there. We are talking about papers written in the 1980s. Okay, so this is not new at all. But once you have the Wilson Dirac operator, which is not a Hermitian operator, any Hermitian operator, you can make it unitary in the standard way. You construct X dagger X and then divide it by that. And this unitary operator is what plays a role, whether you want to compute the anomaly or whether you want to define strictly massless fermions. Under gauge transformation, V goes to that, and under parity, V goes to V dagger. And so the determinant of 1 plus V dagger, the determinant of 1 plus V is the fermion determinant for overlap fermions. You see a determinant of 1 plus V over T, 1 of V over 2 goes to determinant of 1 plus V dagger over 2 with the phase. So this is the relation that I wrote in the previous slide. Determinant of C dagger equals determinant of C times e to the minus I pi eta of A. So the eta, the anomaly, lives exactly in this unitary operator. This is basically what Costa and Lucia did. Okay, so they figured out that you can compute the anomaly, but they only worked with perturbative backgrounds and showed it works out. And later on, Nikhil and I showed that it actually works out in general for any non-perturbative background, and it produces all the right properties. Okay, so this is the lattice Chern-Simons term. So in particular, this also means if you want to write down a Chern-Simons theory on the lattice, it's possible to do. You just have to realize this operator. Okay, and the propagator itself is anti-Hermitian. It is 1 plus V over 1 minus V, which is same as minus A dagger. So this is well known in overlap, so I won't go in great detail. It's not the inverse of the Dirac operator itself that becomes the propagator. It has an extra 1 minus, and so it works out that way. So basically, the point of this slide is to say that on the lattice, we have a faithful realization of the Dirac operator. We have the anomaly, and we have the propagator, which is anti-Hermitian. Okay. Now, you can do everything that I talk about today using Wilson-Dirac operator. It should not be a problem at all. You just fine-tune the mass so that it is 0, and everything should work out. That's in fact how Nikhil and I did it first. But later on, we changed because we wanted to make sure that the tuning of the mass wasn't affecting any physics. Okay? All right. So now I want to talk about some results. And this is the main point. N-flavor QED3 with no monopoles. That means we wrote down the gauge action that is non-compact so that monopoles are suppressed, is scale invariant for all even N. This came as a surprise. So let me briefly tell you why it came as a surprise. So QED3 became interesting when Roth Pisarski wrote a paper saying that large N QCD can generate a mass which is very, very small, which is suppressed by exponentially in 1 over N. But it turned out his paper, which he solved using the Schwinger-Dyson equations, wasn't quite correct. And then Applequest and collaborators worked it out and showed that indeed it does not generate a mass if N is large enough, but then they found out that the solution for a zero condensate was consistent only if N was bigger than a some number. This was sort of incorrectly assumed to say, well, if N is less than that, it's going to generate a condensate. All they showed was that if N is bigger than something, it does not generate a condensate. But then it made it interesting to do numerical simulations, and numerical simulations which were done in the early 90s and even in the early 2000s, they were done slightly differently, and they were either done using staggered fermions or versions of it. And the primary person who did it was Simon Hans, sometimes with John Kogut. And he basically tried to show that there is probably a critical number of flavors. But the way he analyzed it, what he did was that when he did 4-flavor QED, it looked like it probably was not scale invariant. I mean, was scale invariant, but 2-flavor, he couldn't tell. But when he tried to analyze all sort of data in a consistent way, he couldn't convincingly show that it was scale invariant or not, right? So that was the status. And what we did was we used the non-compact. So now I use theta to be different from A because I have suppressed the little A lattice spacing.
Sorry.
So, yes.
Is this model solvable at large N?
Is this model solvable in large N?
That number of flavors, 1 over NF.
Then it's free. strictly in the NF equals infinite limit, it's a free theory. But you are asking for 1 over n corrections, no? Or no?
I don't know. I'm just saying if
Yeah, the 1 over n corrections has been done. That's exactly how Applequest did it. And then in the end of the talk, I will talk about others. 1 over n square corrections have also been done for some context. But the recent papers by Klebanov and others, where they looked at the stress energy tensor, they also looked at the conserved vector current and several other quantities like that, the sort of the anomaly that is present, they only looked at 1 over n corrections. And it just is difficult to do 1 over n squared. So people didn't go beyond that. Yeah. So strictly in the large n limit, it's a free theory. And as n is very, very large, you can do a 1 over n expansion. And that's exactly what people did. And Applequest then basically said, well, what happens if you take the Schwinger-Dyson equations that come from the 1 over n expansion? How far can you push it? And he found that if you pushed it too far down, then it's not consistent with the zero condensate. But then you have to do 1 over n square and see whether it works and so on and so forth. That was difficult to do. So we decided we will do it on the lattice. So here I have to tell you the notation. This is slightly different from the typical lattice notation, but on the other hand, for people outside lattice, it will be almost trivial. So we decided that we will trade the coupling constant for the box size. So we are always in a periodic torus, continuum torus of size L cubed, symmetric in all directions. Capital L is the number of points, and we keep little l fixed and take capital L to infinite to take the continuum limit. And the little lattice spacing A is missing here. That is why I've put theta. Theta is A times the gauge field in the continuum. A is 1 over L. L is the number of lattice points in all 3 directions, and we assume periodic boundary conditions. L is the physical extent of the periodic box in all 3 directions and is measured in units of the physical coupling. So the point of the exercise then is to ask, how does the physics depend upon little l? So what we do, we first take the continuum limit at a fixed physical size and then study the physics as a function of the physical size. So one of the things that we found interesting to do, this is something that I have worked on for a long time, and I found it interesting in many, many contexts. You look at the observable, which are the eigenvalues of the Dirac operator. These eigenvalues are gauge invariant, and they are microscopic, and they have a lot of information. And what you basically do is take the lattice eigenvalues. This bracket means you have averaged over gauge fields, and you have calculated the expectation value. You multiply it by capital L, take the limit L going to infinite, and you call that lambda j times little l. So lambda j is then basically 1 over little l times that, and then you change little and you measure it. Yeah, and the spectrum will be symmetric about 0 because we have decided that we are only using even number of flavors, and we have made sure that parity versus symmetry by saying one of them had the 1 plus v and the other had the 1 plus v dagger. So the spectrum will be symmetric about 0, and it will be a discrete spectrum at a fixed L. So you look at the asymptotic behavior of the low-lying spectrum as a function of little l. Well, if it's free field behavior, it should go like 1 over little l. And so you check if that is true. If it is scale invariant interacting theory, then it should go like, oh, that's a mistake. It's not signed. I meant SIM, and by mistake, I put SIN. It's proportional to 1 over L to the 1 plus gamma m. And the gamma m is what we call as the mass anomalous dimension, which can be anywhere between 0 and 2. 0 corresponds to free field, and 2 corresponds to the case when symmetry breaking has actually happened. It's 1 over L cubed. So the question is, you look at the theory and study it as a function of little l and ask whether it is behaving like this, whether it's behaving like this, or whether it's behaving like that. Now, what I'm going to show you is just a sample data. And the sample data I decided to pick for n equals 2. which is the smallest number of even flavors that you can do. Everything else about that basically behaves the same way. Okay, so here is the picture. Each line there are 4 different capital L's or 5 different capital L's. And what we have done is extrapolated to capital L equals infinite at a fixed little l and got a number. So that extrapolation works quite well. It basically seems to work very well with 1 over L square. And the reason why it's 1 over L square is basically overlap fermions satisfy the chiral symmetry. If you had done Wilson fermions, and if you had tuned the mass to 0, it would have also behaved the same way. It wouldn't be any different. Okay. Now, then what you do here, what I have done is the same plot as here for different eigenvalues now. Eigenvalue 1, eigenvalue 3, eigenvalue 6. I didn't want to put 2 and 4 and 5 because it'll clutter the plot, that's all. And then there are several different capital L's, which has been extrapolated to the continuum as shown on the right. And the behavior looks like this. Yeah. So this is short distance behavior. The short distance behavior is UV, and this is the long distance behavior. This is IR. So we are trying to see as it goes from UV to IR, what happens to this scale. So we expect over here it to go to a constant because I've put on the y-axis lambda times capital L. So far over here, it will be a constant because it's just the UV limit where I'm taking essentially the coupling constant to 0, right? But then when I take L to infinite, it changes. And obviously, this will be a continuous change. And the continuous change we want to ask, as it becomes asymptotic, what happens to this gamma? So if you I know there are Lattice people in the audience. If you try to fit this data, gamma m is not going to be a constant. Gamma m is going to depend upon little l, and the gamma m will start out at 1, and then it will become whatever it is at capital L going to infinite, right? And so here is a picture of what the gamma m is in the limit L going to infinite. And then when we try to do it for n equal to 2, and we do what is called as a chi-square fit, we find the chi-square fit 2 is far away. That's the, don't worry too much about the actual number. The actual number you can get. But the main point here is 2 is far away. 2 is far away, and 2 is what would have told scale invariance was broken. Okay, so this exercise basically tells us that scale invariance is preserved even for 2 flavors of 2-component fermions, which is the smallest you can have without breaking parity. Yeah, and a remark that will become relevant later, if you're very familiar with conformal field theory, you would have immediately caught that the gamma should not go above 1.5 for unitarity to break. So this theory also says gamma is not above 1.5. So the results we have is consistent with the fact that it's probably a correct answer because it's agreeing with the unitarity bound that comes from conformal field theory. Okay, so that's the point. And of course, if you try to get gamma for n equals 4 and n equals 6, it'll become smaller and smaller and smaller till when you get close to n equals 12 or n equals 16, it comes very close to 0. So which is why the large n limit works very well. But the large n limit expansion is not able to predict gamma m, but that I will get to. There is a result by John Gracie where he computed gamma m alone using some ideas that come from statistical mechanics, where he was able to calculate gamma m to 2 orders, assuming scale invariance. Yeah. Okay. So this is basically
what happens for odd n that you cannot simulate? Or
so odd n, there is obviously Chern-Simons term. So that's the main reason, right? So what you have to do then, you have to add a Chern-Simons term to cancel the anomaly, right? So we did this. We did this for n equals 1. So 1 2-component fermion. which has a Chern-Simons term. We decided to cancel the Chern-Simons term using the determinant of V, and then try to do the calculation. Then it turns out that you can preserve parity on the lattice because you have canceled the Chern-Simons term, but it looks like parity is broken for one component, not for three. Just so if you want to say there is a critical number of flavors, it is between, if you think of n as continuous, it's between one flavor and two flavors. Okay, so one flavor QED, one flavor two component QED seems to break scale invariant.
Mm-hmm.
Okay, but that also falls under a slightly different class because we have decided to cancel the anomaly using Chern-Simons. Yeah. Okay. Right. Okay. I mean, you know, there are many other things that you can try, which I am not able to because I don't know how to deal with complex actions on the lattice. But people who can deal with complex actions on the lattice, they can do any odd number of flavors with Chern-Simons term and see what interesting results come out. I mean, these are things that people talk about as developments on the lattice, right? Okay. Now,
and one other thing, sorry, for the overlap operator, the fact that you are using the non-compact gauge field is not changing anything, or?
Oh, you mean smearing?
No, no. So the action, you are using a non-compact version of the action, but in the overlap operator,
for the gauge action.
So in the overlap, it's the same, no?
The theta that comes in the gauge action, the fermion just sees e to the I theta.
Okay.
Yeah.
For the fermion, you use the link directly to construct.
Exactly. And you know, well, Marga, you know very well, we do smearing and all.
Yeah. Okay.
Yeah. Just as a side remark, I mean, I've been following Marga's papers from a long time when she was trying to measure topological susceptibility when she was a postdoc with Pierre Van Baal. So, I mean, this. So I do smearing and everything here. Well, when I say I do, Nikhil did almost all the calculations. I checked the code. His code was always faster than mine. I have to tell you that. So, and also he should be the one really giving this talk. The only reason why he's not giving this talk is he told me that he got invited by your institute to give another talk, which, you know, he has two sides. He also does nuclear physics. And so he gave that talk. So he said, it's okay for me to give this talk. So he gave me the permission to give this talk. So effective action for the gauge field looks like this. So there is the non-compact gauge field, and then there is the fermion determinant, and there is the 2n, which comes from the fact that, oh, I didn't have to put 2n here. This is slightly bad notation. What I mean by that is really n, but n I have sort of thought is 2 times some integer. All right, so we are interested in the action from what we learned before for L going to infinite. And for L going to infinite, we assume scale invariance now, and we write the effective action. By effective action, I mean this along with this, which means this dominates. And we expand in powers of the Fourier transform of the gauge fields, right? So the leading order is unique. The leading order is unique, and this is due to AppleQuest, and this is also the thing that Klebanov works with. Anybody who does large n does this. So what we have done is change the Maxwell action by adding a p in the denominator so that it is scale invariant, so there is no coupling in front. So the little l went away, right? But then if you assume it's parity invariant, you can put order a to the fourth. And order a to the fourth, you can, of course, write an action that is also scale invariant, right? It's possible to do that. I mean, you just have to put 2 times this and say p to some power and p to some other power so that it is scale invariant. Now, we assume, this is important, we assume that the corrections are small. That means this a to the fourth is small, and we attempt to match the results from this action with that of QED3. So what the point I want to make is, this is purely a new model, right? Inspired completely by work that was done before, including results that you can find explicitly in papers by AppleQuest and Klebanov. But what we are going to do is not replace the gauge action by this and still put the fermion determinant, which is what people would have typically done. But we are going to replace the entire action with this. So what we are going to say, the measure for the gauge fields is this. And once we have the measure for the gauge field, we are just going to compute observables. Observables can be pure gauge observables. Observables can be fermionic observables. But there will be no fermionic determinant itself because it has been absorbed in this. Okay, that's the motivation. Okay, now I'll tell you how to match. So the lattice regularization of the effective action, you just replace the P by the lattice P, right? And here you don't have to worry about any doublers because it's bosonic, and you just write down this action and no coupling in front, right? They're just the capital L, which is the number of lattice points which appears here. So you can strictly take the capital L going to infinite here, and it's very, very easy to generate this gauge fields. All you do is momentum, each momentum is independent. So you generate the momentum, and the momentum, each momentum is just Gaussian. So it's just generating Gaussian random numbers and then doing a Fourier transform. You have the gauge fields and you use that gauge field as the background to calculate everything. Okay, so I just want to make sure that people don't get confused and say, oh, what happened to the fermion determinant? And it might look quenched, the calculation, but it is not really quenched because we have absorbed the fermion determinant. Okay, but it's not exact because we didn't put in a to the fourth and a to the sixth, which you could say might appear, right? So we still have some work to do. So before we proceed to look at fermionic correlation functions, we decided to look at Wilson loops, because Wilson loop in a Maxwell action will generate a scale. And but if it is a conformal action, it should not generate a scale, right? And actually, Peskin, long time back, wrote a paper saying what the general structure of the Wilson loop should be, assuming scale invariance, right? In the limit of L going to infinite, okay, in the lattice regularization, right, you get this integral. There might be people working in string theory who can do this integral. It turns out my daughter currently is a student of Andy Strominger, who and they know how to do these integrals very well. So I asked her if she can do this, and she could do it. Basically, if you do one of the momentum integrals, you get hypergeometric functions, and then you get stuck. But you know, that doesn't mean somebody else cannot do it. I could not do it, okay? I have to make that very clear. Since I could not do it, I converted this back into a Riemann sum and calculated the sum and took the limit of the capital L going to infinite, okay? That is my inability, not anybody else's. So after removing a perimeter, right, there is a perimeter which is L plus T for an L by T loop. The result actually depends only on the aspect ratio L over T, which is a precise signature of scale invariance, right? And I will show you this picture now. So that's how it looks. That's how it looks. So in here, this is my inability to do the complete integral. So I did 64, 128, 256, 512, and then it approached a limit, and that limit is right here, and the x-axis here, after we removed the perimeter divergence, is exactly aspect ratio, and you see it falls on the aspect ratio because there are many, many Wilson loops here, all kinds of L and T. But when I multiply and only put L over T, it comes that way, right? And then the slope, which you could have calculated it exactly if you could do that integral. I could only do it this way. And because of the fact I had to extrapolate and things like that, there is a small error here. And that is basically the statement. There is an L going to infinite at each aspect ratio, and the dependence is only on the aspect ratio over the entire range. And this number, you can sort of say, is conformal data because it tells you what is the coefficient in front of L over T. Of course, it's a function of L over T, so that when L over T is very large and when L over T is very small, it's this number. In between, it's some complicated function of L over T. Okay, so this is the first evidence that, but this is probably not a surprise because we wrote down a gauge action that was conformal and we calculated something that you expect to be. Now, in this model, you can actually compute correlations of Wilson loops, and correlations of Wilson loops also will be non-trivial. But what is missing here is if you try to take n point functions of Wilson loops, that means you put n different Wilson loops and try to get the expectation value, I don't think you will get the correct answer. The reason is that there, I think a to the fourth and a to the sixth will matter. Okay, but then I don't know in QED how important that is. Okay, that's the question we are asking. In general, it might be important, but in QED, even for n equal to 2 flavors, that might not be relevant. That might be very small, and it's completely suppressed. Okay.
Sorry,
Right.
I don't understand.
Yeah. Yes, Tony.
Question.
Yeah.
I'm not sure I understood completely. Can one not do these calculations directly in the original theory, not in the model?
Oh, in QED3.
Yeah.
Yeah. You can do that. You should get the same answer.
But did you do it or?
We did this. Yes.
Oh.
Yes. We computed the Wilson loop. Yeah. We computed the Wilson loop and showed this. Yes.
Okay.
Yeah. But Tony, I you know, here
There you have everything.
I want to say I have a with modulo my inability to do the integral. This is a much better result than what you will get from QED3.
Okay, fine.
You see, because I won't be able to go to 512 cubed lattice, right?
Mm-hmm.
Yeah, that's all. Yes, you're absolutely correct. But keep in mind, Tony, there it's only in the infrared that you will get this result. In the ultraviolet, you won't. So you also have to flow from the ultraviolet to infrared to get this result. Here, I don't have to do anything. It's just a result that comes. There is no coupling, right?
Okay, sure. That's
yeah.
right.
Yeah. So, so this is important. The observables are computed with this measure. Okay. The parallel transporter is again e to the I theta, and there is no fermion determinant. So, an lattice calculation basically looks quenched. And plus minus forms parity partners, as I discussed before. Okay, so it's either 1 minus a or 1 minus v over 1 plus v, or v minus 1 over v plus 1. The Dirac spectrum, again, as I told you, the eigenvalues have to come ordered, right? We are interested in the limit L going to infinite, but now you see in the compact gauge field, I've put in a Q. The Q, if it's very, very, very small, you can sort of match it to 1 over n expansion. But we are going to assume Q is free to vary. Q can take on any value, okay, not necessarily small. And we are going to ask what the result looks like. That's the key point where we are departing. So which means we are not relying on a 1 over n expansion here. So correlation functions you can calculate of parity triplet scalar mesons. Like that, you can put in a plus minus minus plus, or you can put a plus plus, the 3 of them which forms the isospin triplet. Or you can calculate the vector mesons, which is this. So you can either look at the eigenvalues, or you can look at the scalar mesons, or you can look at the vector mesons. So now probably I will be answering the question which Tony was alluding to, which is you should be able to get these results in QED3 also. That's precisely the point here. Okay, so let's look at the Dirac spectrum. So the Dirac spectrum now looks like this. Okay, the only parameter is Q. There is no box size. It's just the number of points on the lattice, which goes to infinite. And there is no small l and capital L. As a function of capital L, you should simply find, you see, its scale. In the log L plot, it should become a straight line. And now, where it becomes a straight line, of course, has to be in the continuum, which means capital L has to go to infinite. So, there is no free lunch theorem. If you want to make Q large, you can imagine, because you have put e to the IQ, it's essentially like large Q means large lattice spacing. which means you have to take capital L to infinite. But once you take capital L to infinite, it's an exact result that you will find as a function of capital L, it will go like a power law. So there is no fine tuning here. The model is the model. You just put in L, which is the number of lattice points, calculate the eigenvalue as a function of Q, take capital L to infinite, look for scaling, see if it matches. Okay, so this is not something that you expected in a lattice theory. Okay, so now for technical reasons, it's better to look at the eigenvalue normalized with respect to the free theory, because then you are finding departure from the free theory, right? And there is only a dependence on L, right, at a fixed Q. The fit takes the form, this, and the reason why it takes this form is because the Dirac operator doesn't have to just couple to the primary field, yeah, from the viewpoint of a conformal field theory. It can couple to other operators that are subleading. And so in order to extract the sort of the leading conformal dimensions, you need to assume that there are some subleading ones. Like, if you have 5, probably you have derivatives of 5 and second derivatives of 5 that have come in there simply because, we put in a Dirac operator with a finite difference, not a continuous derivative, right? So we have to do that. And that was exactly what is done. And here is the picture of how the conformal dimension looks for this operator as a function of Q. This in principle is continuous. So we have done many different Qs, and that's the error bar, okay? It's tiny, the error bar. And the reason why it's tiny is because it's very, very easy to generate gauge field configurations, right? And these were done on desktops. These were not done on clusters, okay? If you decide to do on clusters, you won't see the error bars here at all. So you can really nail this down and get a curve that is perfect, okay? What we have done here is try to match the data, which is what Tony was asking in the context of Wilson loop, with what you got in QED. And you see in QED, the error bars are really big. The error bars are really big because the vertical, so the vertical one is QED, right? That's that big in each end, right? And then what we did is we simply, using the vertical scale, we put in a horizontal scale so that we went through the curve. So you see, this tells us that if you want to match with QED3, QED3 has to be done much, much better. So there, the numerical data has to get even better than what we did so that this rectangular box can be nailed down to something. And why would we want to do that? We would want to do that so that we can map Q to N, okay? Which is not expected to be a simple 1 over N or a 1 over N square correction. So this curve, which I show using the black dots and extrapolation, is what is done using the conformal field theory model on the lattice, which can be done. Then if you want to match to QED, which at this point somebody might say, why do I have to do that? I already know how to do some conformal field theory data. Let me proceed. But if you do want to match with QED and say which Q corresponds to which N, this picture shows you that the QED results have to be improved so that the vertical errors go down by a factor of 4 or something like that so that it shrinks. By a factor of 4 is not such a big deal. So this is motivation for somebody to, including us, to sort of see if you can improve the QED data itself, okay? And Tony, this also tells you why, if you try to measure Wilson loops, it'll have the same problem. The data won't look so good as I showed you in the previous picture, yeah? Okay, so that's, yeah. So this gives a map between N, the number of flavors in full QED3, and the Q in the conformal field theory on the lattice that we studied here. Okay, so that's the main point of this slide. So we can get the map. But to do this, you really have to do numerical analysis of QED. You know, way over here, you might be able to get a 1 over n expansion. If I decide to plot the 1 over n, it'll start deviating here. If I put 1 over n squared, it probably starts deviating somewhere here. Okay, so if you can get more and more terms in 1 over n, it probably can be matched too. Okay, but the question that comes back is, do we really need to do this if all you're interested in is getting some conformal field theory data for an interacting conformal field theory, right? So at any point in here, it's a conformal field theory that's interacting. So you can get the data. Okay, so now I want to continue on to show that the agreement we are getting is not just with one. And the reason why I want to do this is because, remember, I have sort of set a model that says that there is only the quadratic coupling in the quadratic term in the gauge fields. So if there are other terms, then the other terms should say, well, if you agreed with one, it doesn't agree with something else. You will need to put the other terms in. So there is another free parameter. So we looked at, again, the departure of the scalar correlation function from free field to whatever. We first take, again, the L going to infinite. And then here is the interesting thing. Once you have taken L to infinite and you look at X, okay, X has to be really discrete because we did it on the lattice. So 1, 2, 3, etc. Well, it will exhibit scale invariant behavior for all X. But the only problem is because our operators are not pure primary scalars, in the beginning, when X is very, very small, you will have contamination from secondary operators. But then as X goes to infinite, the primary operator will dominate and you will get the primary scaling function. So that's the idea here. Okay. So what we do then, thinking about it like that, we look at this scalar correlator at a fixed number of points. We look at it at a fraction of the scale. When you do it at a fraction of the scale, you see when you say it has some power law, well, it's going to be rho L to that power. So it's going to be L to that power. And then there is going to be something that is only dependent upon the scale factor, nothing to do with capital L. So that's another way to extract. And if you extract, here is the picture on the right. And the right picture is just data. That's what I want to say. The right picture is just data, no lines. The left picture was what I showed before, and I got the gamma from that. Once I got the gamma from that, I simply used that gamma here and plotted this line. Okay, so these lines are directly from the points here. Okay, no change. So this is not a new fit. It's simply the gamma obtained from the eigenvalues put into this to see if it agrees, and it agrees very well. It agrees very well all the way up to where the Q is the largest. Yeah. So left figure was shown before and shows the scaling of the lowest eigenvalues from which we extracted gamma. The right figure shows the behavior, and we picked rho equals 1/4, and the slope of the lines correspond to the scaling dimension that we got from the left figure. So it agrees. So which suggests that the model probably is able to reproduce the data all the way up to this value of Q, which corresponds to, from the previous picture, n equals 2. So it's probably going to describe the entire spectrum of QED for all flavors. Okay, let's see some more. So now there is an interesting result, and this interesting result has become relevant these days because everybody is talking about the so-called web of dualities in 3 dimensions. And this is an example of the web of dualities. So if you look at the vector triplet correlators, because it's a conserved current, the scaling dimension is unchanged. There is no anomalous dimension, but there is a constant in front. This constant in front was actually computed by Klebanov and company. And when they computed it, we tried to verify whether we get the number they got in 1 over n. And we found that at n equals 2, there is significant departure away from the 1 over n calculation that Klebanov and company did. So when we did the QED result, the n equal to 2 result for vector triplet correlators was new, in the sense it was something that you couldn't get in the 1 over n expansion. So again, we do this. Now the point is, because of the fact that if you change Q, the power law doesn't change, the ratio should not depend upon X. Okay, should not depend upon X, and it should simply be a constant. But of course, it's not a constant because it's not a perfectly conserved current. We only have an operator that becomes conserved in the continuum limit. The Lattice fermion bilinear operator is not exactly conserved, but it couples to the conserved vector current. So we expect this to reach a non-zero value as X goes to infinite, and that depends upon Q. That would be called as the conformal data, which is basically the coefficient that sits in front of the 1 over X to the 4th. Okay, that coefficient you can get, and here is the coefficient we are getting, and it's close to 1 when Q is small, and as Q becomes more and more, and now you see we are having already a little bit of difficulty trying to get the flatness in Q equals 2.5. So whereas things looked nice numerically in this model, now at 2.5, it looks like desktop computers are probably not enough. You actually need to do a little bit better to get this data, but it's very, very easy to improve this data. Okay, so triangles are L equals 28 in here, and circles are L equals 48. And you see, basically, we have gotten rid of the finite lattice spacing effects. So that's not the problem here. It is the deviation away from the primary operator. So a plateau is seen, and I say Q less than or equal to 2. So I'm going to ignore the Q equals 2.5 because there I can't get, right? Now, here is the interesting result. So if you take the CV effective and divide it by 1 over 4 pi square, which 1 over 4 pi square is basically what you will get for the free field, and you compute it with the what is called as the topological current correlator, which is the current formed out of the gauge field, which is basically this, then the enhanced symmetry says that this set of 3 forms a partner with this 3 to enhance the symmetry. And so the dual currents and the currents themselves have joined together. Okay, and you see, if you try to calculate this curve, the bottom curve is a trivial curve. It's just the calculation of the F mu nu correlator in a quadratic theory. So this one, I can do it on a piece of paper and get the answer, right? This one, on the other hand, is data that comes from our calculations using the conformal field theory model. And you see both of them join very close to Q equals 2.5. So CV equals CV top is favored by Q equals 2.5. And now I put in the bottom picture, the connection between gamma and n, and then within errors, it's consistent with n equals 2 QED. Of course, more work has to be done to calculate this better and get that point here found very well. And then if you also improve the QED data, you will be able to show quite well that n equals 2 QED is in fact an enhanced symmetry where the...
Can I answer a question?
Yes, yes, Tony.
You can also do Q different from 1 in the QED3 theory directly, right? By putting the link to a power.
You mean, sorry, say that again. I didn't catch.
Q is the charge, right?
I see. So what you are saying is, suppose if I take the the gauge action in QED, I can write down a theory not with charge 1, but charge 1.5.
Exactly.
Well, now, if you don't put any other charge, that charge can be absorbed into little l. And so you can change the trading, you can trade little l from, the gauge coupling can be traded into the thing. So unless you put two different charges.
I changed just in the determinant. I mean,
yeah, but yes, you can, but then,
the gauge action stays.
You can show, you're absolutely correct, but then I can make a change of variable Q theta to theta, and then when I put it into the gauge action, it just changes to little l.
Yeah, up to, maybe.
But Tony, this is only if you have one type of fermion. Yeah. I can do QED with charge 1 and at the same time charge pi fermions.
Yeah, I agree.
That we didn't do. Okay.
I agree.
That we didn't do.
I mean, that we didn't. If it was compact, maybe it's not, but it's not.
Compact is a very, very different story. I can talk to you for a long time. If I was actually in Madrid, that's what I would want to talk to you about, because we could not do compact QED. That's the short answer. Okay. I can tell you in great detail, but the short answer is we could not do compact QED because monopoles cause a lot of problems. And if you try to do Wilson fermions, you are not even able to tune the Wilson mass to 0.
Yeah, thank you.
Okay, but that's a long story. So we were unsuccessful. Okay, now we can do better in matching with QED3. Okay. So what I showed you there was just looking at the eigenvalues. But this is the beauty, which some of you already know, people who are doing Lattice. There is actually a distribution of this eigenvalue. Okay. So you calculate this eigenvalue per gauge field configuration, divide it by the average, which is called the scaled eigenvalues. That has a distribution. And this distribution is supposed to be universal. Yeah. And no assumption is made on scaling behavior now. I am not fitting, this to some gamma and then trying to match with QED. Instead, what I do is I have shown you these three, the model 2.5 with L equals 32, L equals 28, L equals 24. This is the data that we just got. Yeah, you see it here. At the same time, this is old data with two flavors and L equals 200 and L equals 144, little l, I mean. There we had to worry about the gauge coupling, right? And you see, they fall on top of each other. And this curve here is a curve that you would predict if scale invariance was broken. So this data, as shown here, without fitting to any anomalous dimension, shows you that there is scale invariance here because it didn't agree with RMT. Furthermore, because you have a distribution, you have a better way of matching Q to N. Yeah, and here is the first eigenvalue, the second eigenvalue, and the third eigenvalue. And if you do Q equals 2 and N equals 8, again, it matches quite well, the first and the second and the third. Now, if instead you had decided to put for N equals 8, 1.5, it will not match, you see. That is the data of the model. That is the data from QED3. It does not match. So by using a full distribution and matching point by point on the distribution, you can actually get a better way of matching Q to N. So I think if we do this, which we intend to do, then you will get a better map of Q to N, okay, with the data that we already have, all right? And here it turns out Q equals 2 favors N equals 8 compared to Q equals 1.5, okay? So, and I again put the unitarity bound and the plot from the gamma, and you see this picture sort of give a big rectangular box, but if you compare this and this, it looks like it's much better. So there are better ways to do this, okay? Now I want to talk about a little bit more. This is just a few minutes. And I want to say we can extract more conformal data. We can actually calculate 3-point functions. And we calculate 3-point functions, and 3-point functions in conformal field theory are very well known. And it's also well known that if the 3 points are collinear, the formula simplifies very much. For example, if you have the vector triplet plus minus 0, then it's conserved, but then you have a constant in front. If you do this one, you get the B. If instead of all of them being in 3 direction, if one is in the 3 direction and the other 2 are perpendicular to 3, and if you do 2 scalars and a vector, you get a C. So, and you also have the anomalous dimension here because you put in a scalar. So in 3-point functions, you get these well-known numbers for the 3-point function in conformal field theory, and we can extract that too. That's the main point of this result. So without talking about the details, which is here, right? We find plateaus, and the plateaus sort of say that A, B, and C can all be extracted, okay? And we find, not surprisingly, that in free field theory, A is 0, which means these two are the same, and B is B naught, but we find B to be different from B naught, because if you look at this V1, 0, it's far away from 1, and so this B is different from B naught, and at the same time, A plus B is different from B because these two are different. So we have shown that A is not 0 and B is different from the free field theory, okay? And non-trivial dependence on Z2 is there because we picked different Z2, which can change this function, but it looks like a plateau, okay? So 3-point functions can also be done, and I want to emphasize this was not done using big clusters. This was basically done using 8-node machines and 16-node machines, which we have in our office, and we did it, and that's all that was done. Not much more effort. So you can imagine if you try to do using a large cluster, you can get this data quite well. Okay, now for sort of inviting people to collaborate with us. One could look at other operators to get more conformal data, right? And Tony kind of alluded to this. For example, I can write down a 4-point Fermi operator where the charges are not the same, they are different. Q1, Q2, Q3. And I made sure that it's gauge invariant by putting this charge to match with these 3 charges. And I can write down another operator like that, and a third operator in such a way, when you look at all 3 of them, there is a Q1 here and a Q1 here, and a Q2 here, and a Q2 here, and a Q3 here, and a Q3 here, Q4 here, and a Q4 here. And this charge is matched with this charge is matched with this. So we can write down operators like this. It's just calculating, propagators in a quench theory. It's not very difficult to do. We haven't done it yet, but it can be done. And then you can try to calculate. And if you look at there is no 1-point function for this. There are 2-point functions, and the 3-point functions will have only connected piece. So it's very easy to do on the lattice, and then you can get more interesting conformal data. Yeah. So I think this is kind of a nice way to try to get information on an interacting conformal field theory. Okay. And you can make this into a vector or a tensor operator by inserting 1 or 2 sigma matrices. So you can use conserve properties and so on and so forth. Yeah. What else can we do? Well, it turns out, if you look at the numerical data for gamma S, it seems to go very well with Q square and Q to the 4th. This does not mean 1 over n and 1 over n square works very well. Q is not equal to 1 over n. Q itself has an expansion in 1 over n, okay? But in Q, it seems to work quite well. So my hope is that we can do this, but then I don't think we can do lattice perturbation theory. I did a very simple calculation. In lattice perturbation theory, you will have 4 3-momentum integrals to do, and 4 3-momentum integrals is an L to the 12th computation. I have done perturbation theory calculations in my young days, but this is not an easy thing to do. So I think here we probably have to do something else. As I said, the numerical simulations for this paper were done essentially using a few nodes. Generation of gauge field configurations is very easy. You just generate it in momentum space and Fourier transform it. So that's easy. Now, the point I want to make is Gracie, whom some of you might know, computed the anomalous dimension or the mass anomalous dimension in QED3 up to 1 over n squared by assuming scale invariance. And the trick is based on an old idea by these three people who told how to do, so it sort of goes back to how Wilson tried to calculate scaling dimensions, right? You sort of assume that it's Schwinger-Dyson equations, but Schwinger-Dyson equations not to extract a gap, but to simply extract the anomalous dimensions, right? So you write down equations for gamma and try to solve gamma, okay? Now, they only did gamma sub n. Can we just do this for everything else? For example, can we then continue with this model and do just a continuum theory calculation and follow the ideas that are here and extract more conformal data? That's the point I'm trying to get at here. Could we adopt the method to the model developed here so that we don't have to do a lattice calculation at all? I mean, I am a lattice person. I do calculations in the lattice, but as far as I'm concerned, the point is to get the result. So if something else works, I would rather do that, okay? And here we are clearly interested in collaborators who want to think about this. And I thank you for listening to my talk, okay? Thank you very much.
Okay, thank you very much, Professor Narayanan, for this very nice talk. So are there more questions or comments?
Yes, I have a question related to the distribution of eigenvalues that you have shown.
Yes. Yes.
So how did you do this in practice? I mean, did you have to rescale to take into account the change in lattice size? I mean, is this a comparison at fixed lattice?
Yeah. So give me 1 minute. Let me go to that slide, okay?
Yeah.
Let me go to that slide. Yeah. And let me just share. I don't have to show it as a PowerPoint. So this picture, right? This is the picture you're talking about?
Correct, yes.
Okay, yeah. So yes, so this scaling, this is done basically to get rid of any lattice spacing effects, because all lattice spacing effects are in here, right? Once you have done that, you will still find in the distribution, it doesn't agree very well at, say, 24, 28, 32. You still have to take capital L to infinite, okay? And in QED, you still have to take little l to infinite. But the distribution itself, so when I did this for QCD, what I would do is there, Jack Werberschott and collaborators starting with Shuryak figured out the formula for the distribution. Basically, it's some Bessel functions and derivatives thereof, right? So I would get that and I would match it point by point to this and fit it to one number, right? And that was the idea, which would be this denominator here, right? Now, that's not the point because I don't know what the distribution is because scale invariance is not broken. All I know is there is a uniform distribution and mathematicians don't know the formula for that. So I am just extracting it, okay? Does that answer your question?
Yeah, so I had in mind this work by Verbaschop and collaborators in which they have seen that when they go to the lattice, there are corrections to the continuum form, which depends on some low energy constant of chiral perturbation theory. So,
exactly. Yeah, except that now we don't have chiral perturbation theory at all here because scale is not broken. So I don't know the formula even in the continuum here.
Okay.
Yeah, but you are referring to exactly the right papers. So when we did it in QCD, we can do exactly what you said. But I don't know how easy it is to extract f pi this way. Okay. I haven't tried to extract f pi. I only tried to extract the condensate this way.
Okay, very good. Thank you.
Yeah.
More questions? I have a naive one.
Probably not.
So people must have studied this model QED3 in the epsilon expansion, like
Yes.
Wilson Peter.
Yeah. So Klebanov did both epsilon expansion and 1/n expansion.
And what is the answer there? I mean, do you get formal symmetry at all n, or is there a critical n or something?
Right. So what happens there is that very close to n equal to 2, they are not able to predict. So Appelquist basically said that it is somewhere around, if I remember correctly, it's close to 4 pi or something like that. Yeah, which is what he predicted as the critical coupling. But that died very fast. People who did numerical simulations found it's not something like that. It's probably somewhere between 2 flavors and 4 flavors. Okay. Then recently, and I say recently, I mean 3-4 years ago, it became interesting for string theorists to do this. So Klebanov did it, and Klebanov did it, Pufu did it, several others did it in that group, in the Princeton group. And they basically said, whether you use epsilon expansion or 1/n expansion, it seems to be consistent with the scale invariance all the way up to n equal to 2, but n equal to 2, they were not able to tell. So when I gave this talk in Princeton a while back, and the string theorists are comfortable with the result that it is scale invariant. I mean, it's two-edged sword. If it wasn't scale invariant, you had a very nice model where you could study the transition to scale invariance from scale breaking by just tuning the flavors, right? Now that's not possible in QED3. But in QCD3, it's possible. In QCD3, there is clearly a critical number of flavors.
Mm-hmm. And this implicit relation between Q and N that you keep talking about, is there some approximation in which you can analytically control it, like the 1/n expansion? Can you give a formula for Q?
In 1/n I can give, yes. 1/n we can give. And I'm trying to understand Gracie's papers. For people who have looked at it, they are not easy. I mean, it's quite involved. First of all, you have to write Schwinger-Dyson equations, and then you have to solve these couple Schwinger-Dyson equations for these anomalous dimensions. I'm trying to understand them. If I succeed, then I will be able to answer your question better. But in principle, the leading order is very easy. The leading order is very easy. That we checked. We put it in the paper. There is a relation between Q and N. I forget now exactly what it is, but it's a simple relation. Yeah.
Mm-hmm. Yeah. Okay. So are there more questions? All right. So if not, I would like to thank Rajamani again. Thank you very much for this very nice talk.
Thank you.
I clap in the name of the people. And I will just stop the recording now.
Thanks. Okay. Thank you so much. And thank you everybody for attending. Yeah. Okay. Hope to see you.